Here we have a one-shot color light master from PixInsight's weighted batch pre-processing script. The object is IC2574, Coddington's Nebula, named before astronomers realized it was actually a galaxy. I performed a gradient removal and applied a screen stretch so we can see what we're working with. The image is still in its linear state. The image has some problems. We can see a dust donut, some horizontal banding, and several other artifacts scattered across the field. Unfortunately, I no longer have a matching flat, so what to do? One answer is to build a synthetic flat and apply it to the image. The idea is simple. Instead of using a real flat field, we're going to derive one from the image itself. In this way, we will calibrate out the artifacts that the original flat either introduced or failed to remove. To build our synthetic flat, we first need to create a starless version of the master. I use Star Exterminator for this. You can use whichever star removal tool you prefer. Here is our starless result from Star Exterminator that I ran earlier. You can see the problems even more clearly now the stars are gone. Dust donuts, banding, gradients, and other artifacts stand out clearly against the background. This starless image is going to be the foundation of our synthetic flat. The next step is to carefully remove the astronomical detail from the synthetic flat. We need to do this because the object would contaminate our flat field. To remove the galaxy and other genuine astronomical objects, we can use clone stamp. I use clone stamp with a radius of 50, opacity of 0.3, and softness of 0.75. I find that the opacity setting is particularly important. At 0.3, each stroke only replaces 30% of the pixel values, which helps with blending against the surrounding background rather than making a hard transition. The softness of 0.75 feathers the edge of each stroke, reducing hard circular boundaries where strokes overlap. Sample from multiple surrounding background regions, but close to the object so as to match background brightness, moving around the object rather than always cloning from the same spot. The more carefully you do this step, the better your result, although we will take care of minor blemishes with the next step. Take your time here. This is the most skill-dependent part of the whole process. Here is our synthetic flat after the clone stamp step. The galaxy has been replaced with sample background and the dust artifacts are clearly visible across the field. The next step is to apply a multi-scale median transform, or MMT, to the synthetic flat. This is a wavelet-based decomposition that separates the image into layers, representing structure at different spatial scales, from fine pixel level detail right up to very large broad features. We want to keep only the large scale structure in our synthetic flat. That is, the dust donut signatures and illumination variations, and discard everything fine scale, including noise and any subtle brush marks left by the clone stamp step. MMT does this cleanly because, unlike a simple blur, it preserves large-scale features while genuinely removing fine detail rather than just smearing it. I'm using 5 layers here. I disable layers 1 through 5. These represent structures from 2 pixels up to 32 pixels in scale. The residual captures everything at larger scale than 32 pixels, and this is where our dust mote signature lives. I find 5 or 6 layers work for me. If your artifacts are smaller, try 4 layers. For very large-scale artifacts, try 6 or 7. Here is our synthetic flat after MMT. Now we are going to apply our synthetic flat to the original image using pixel math. The expression we use is $t times the median of the synthetic flat divided by the synthetic flat. Let me explain why this is better than simply dividing by the synthetic flat directly. In a perfect world, we could write $t divided by synthetic flat and be done with it. But think about what a real flat field looks like. It's an image of a brightly illuminated panel or sky at about 30 to 60% of camera saturation with significant pixel values across the whole frame. When you divide your astro image by values close to 1, almost nothing changes, which is what we want. Just the subtle variations in the flat doing their correction work. Our synthetic flat is different. It was derived from an astro image, so its pixel values are tiny, just a fraction of what a real flat would show. Dividing by those tiny values would be like dividing by nearly 0. It would multiply the image brightness by a large factor, and the result would be a completely blown out white image. The median synthetic flat term fixes this. By multiplying by the median of the synthetic flat before dividing by the synthetic flat, we effectively normalize it, rescaling it so the average pixel acts as if it were closer to 1. Now the division behaves like a real flat field division, with the variations around the average doing the correction work, but without the overly bright result. Here is what each part of the expression does. $t means the target image, whichever image is selected when you run pixel math. In our case, this will be the original linear master. Synthetic flat is the name of our synthetic flat image as it appears in PixInsight. Median synthetic flat is that single normalization value calculated from the synthetic flat image. Where the synthetic flat pixel value equals the median in a clean, unaffected background region, the correction factor is exactly 1, and those pixels are completely unchanged. Where the synthetic flat is brighter than its median, at dust donut locations where the artifact pushed pixels value up, the correction divides those pixels down, removing the artifact. Where it is darker than the median, it brightens slightly, correcting the opposite type of artifact. The result is a flat correction that removes the artifacts without changing the overall brightness or color balance of your image. Here is a synthetic flat corrected master. As you can see, it has corrected the dust donut, reduced the horizontal banding, and improved the overall background uniformity. The galaxy itself is untouched. The correction was neutral in that region. We can compare the original master with the corrected version. From here, process as normal. Noise reduction, nonlinear stretch, color calibration, star reintegration, whatever your usual workflow looks like. Of course, it would always be better to have used a correctly matched flat field in the first place. Clean optics, flats taken at night on a flat panel, matched to the actual session. But when that's not possible, and you have an older session with artifacts you can't recalibrate, this approach gives you a practical path to a clean result. I hope it helps. If you have any questions or want to share your results, drop them in the comments below. Clear skies.